not the dash square, but the top, this square together with this square. So the very first entry down, the very first entry in the x direction corresponds to x frequency equals 0, and the last one, or in other words, the frequency is the index over n, except worry about the 1. Okay, so we learned that. Any particular frequency is the corresponding index over n, where n is 128 in your. And the indices run from 0 up to n minus 1, which is to say there are n entries in the x direction, and go to 0 to n over 2 in the y direction, meaning there are n over 2 plus 1 entries in the y direction. But be careful about the MATLAB conventions for where the indices are, whether they're at the top or at the bottom, and whether they're, but this is using ordinary mathematical notation of these arrays rather than the MATLAB order for the arrays and indices. Okay, but this guy, the one going from n over 2 plus 1 up to n minus 1, you need to subtract 128 from the index, meaning this guy actually mathematically belongs over here. Right, so the actual k's that you're going to use are the k's from here, which are negative over here, and positive over here, and positive in the y direction. Does that answer your question?
That helps.
Yeah.
The reconfiguration.
The what?
The extra program, the recon at phase, that takes care of the flipping course, right?
Oh, does it? I'm sorry. Mike, do you know whether that's the case?
I'm sorry, I wasn't listening.
He says that this guy over here actually, in amp phase, appears over here. In other words, it has negative frequencies followed by positive frequencies.
I don't remember that's the case.
You can check that for you. Okay. You can check that for yourself.
Yeah.
Hold on, I need to admit. What happened here? I'm trying to admit. One of the members of the class is ill, and
That bar just
there
works.
she is. Okay, so put in an ordinary cosine function in x, cosine of 2 pi 1 over x. The cosine has a plus frequency and a positive frequency and a negative frequency, right? Cosine is e to the minus cosine of 2 pi anything x equals, I'll go new, is e to the minus I 2 pi minus nu x plus e to the minus I 2 pi plus nu x over 2. It's the sum of a term in frequency nu and a term at frequency minus nu. And so if you run that into the program, you will see where, and you do it for example, nu equals 1 over n. You should see a response in amplitude only at frequency 1 and at frequency -1. And you'll see where those live on that array, and that's a way to check which order it's coming out in. That answer the question satisfactorily for you? The problem is that the DFT program itself, as gotten from the web, does what I just said. It has the positive, the high index frequencies in X actually corresponding to negative frequencies. But we may have, the program that was written a couple of years ago, and I'm sorry, I haven't checked it myself recently, may have compensated for that and actually done the flip for you.
No, I think you're right.
I was right in the first.
The high frequencies are the negative ones.
Okay, the high frequencies are the negative ones, so you have to do the flipping. Well, the flipping in the sense that when you read out a frequency that's bigger than, in this case, 64, bigger than 64, starting at 65, when you have an index that's that, you have to subtract 128 from it. So the 65 really corresponds to -63. Other questions? Okay, so first of all, apologies for changing assignment late, but there were some typographical errors, and there are, the LAs suggested that it'd be a fairer way to grade you if instead of asking you to pass in one program where if you have a screw up anywhere along the way, you don't get credit, to pass in 3 programs, which are the pieces going on along the way. Okay, and so the MATLAB grader is going to expect 3 programs, one of which takes the original image and the RMS width, the standard deviation of the Gaussian, sigma, and it will produce a magnitude and phase image of the Gaussian applied to that image, right, in the frequency domain. So after the Gaussian's been applied, it should yield both the magnitude and the phase, and I'm asking you to output the magnitude only, but to be able to pass the magnitude and the phase to step 2. So the first program just produces a magnitude array and a phase array, and you'll be graded on the magnitude array, if you will. The second one produces the magnitude, takes the magnitude and phase array, and back in the space domain, produces the XX derivative, the XY derivative, and the YY derivative images, right? And the output that you'll be graded on is the XY derivative. So you output just the XY derivative. Okay, but pass all 3 of them to the rest of the program, which will require you to take those 3 image values and pixel by pixel produce a bar strength of that pixel. And so you'll output the bar strength image. Yeah.
So we do the bar strength calculation not in the frequency domain after we transfer it back.
That's right. The bar strength cannot be computed in the
And
frequency.
the second one is also already switched back from frequency domain as well.
I didn't say it. Speak.
The second question,
Yeah.
we've already switched it back from frequency domain for that question too.
Yeah, that's right. These are images in X, in position. Ordinary space domain images. Whereas these, as it says here, are images in nu. In the same arrangement that they come out of the mag phase, which is to say the negative frequencies have to appear up there in the higher positive index locations. Any further questions? Yeah.
We're no longer taking the derivatives in the frequency domain.
Well, you're certainly taking the derivatives in the frequency domain.
So the second
This
step,
second program goes from here, computes the derivatives in the frequency domain, and then transforms them back into the space domain. So there's two actions that have to be applied to get from here. Well, 4 actions, one that produces the xx derivative, one that produces xy, and one produces yy, all in the frequency domain, and then the inverse Fourier transforms of all of them. Okay? So I haven't said what's going on in each of these programs. That's for you to show you understand. But I've told you what the inputs to each of these programs should be and what the outputs should be. What the results should be. Okay? And in order to accommodate the fact that I've changed it so much, I've extended the due date to a week from today. It was due Thursday, and now it's due next Tuesday. Okay? Apologies for the changes, but I think it'll produce a fairer grading for you, so you could get credit for exactly. If you make a mistake in one of the programs, you'll only lose credit for that piece. Okay? Any other questions on anything? Okay, I'll explain why, but I also made an error when I told you what the definition of Rms width is. And so I want to correct myself and explain the story. Okay, so this, so first of all, if you have a kernel H, it may be in 1 dimension, it may be in 2 dimensions, it may be in 3 dimensions, right? And it's just some kernel function that you're applying to some image. And you want to know the width of that, the so-called RMS width of the kernel. You, first of all, compute the center point in 1 dimension for a Gaussian. It's here. It's sometimes called the mean of the kernel. And it's defined simply as the integral of fix that. That's a mistake. The integral of x, h of x dx. So it's just the average of x, h weighted average. But since h may not have unit integral, you have to divide by the integral of h. If h has unit integral, you don't have to do that denominator. Okay? So this is x bar, also sometimes called mu. Black pen. Strictly speaking, you should be careful, or I'll try to be careful. The mean is the mean of a continuous function, h. And the normal way you compute a mean when you have a bunch of examples is to take the sum of the examples and divide by n, right? And that x bar is strictly the so-called sample mean, the sum of the examples divided by n, and the mean mu is defined in terms of the continuous integral. They approach the same as the samples get closer and closer and closer, right, as you have more and more and more equally spaced samples. All right. But anyway, now that you have this mean, you look at every point x and take its distance to the mean. And so now you have, for this x, this distance here in 1D. In 2D, if you have a circle, let's say, then that distance is the x component of this squared plus the y component of that squared, right? But in any case, it's the square of the distance to the mean. And this has to be normalized by this integral of h if it's not 1 already. So it's the h-weighted distance squared. And that is what I should have given you as the definition of the RMS width. However, I gave you a different definition last time, and it's this one. If you have a positive h of x, like the Gaussian, you can take an integral, the average width from here to here at every height, from height 0 to height h max, right? And so we're talking about this width, which is the value of it, the value at x that gives you this h on the positive side minus the value on the negative side. So it's the average, the width. And so when I say x super plus of h, I mean this, if you're talking about this h, x super plus is this, and x super minus is that. It's the two values on the positive side of the mean and the negative side of the mean. And here you're normalizing by 1 over h max. And the interesting thing is that this RMS mean, which is this average square to the half, that's the R in RMS for root mean squared. This guy is sigma for a Gaussian, and this guy is sigma for a Gaussian. Okay, they both give you the sigma of the Gaussian for a Gaussian, but it's not, that equality is not necessarily true for non-Gaussian functions. And so in particular, for the rect function, what's the average width? If the rect goes from minus delta x over 2 to plus delta x over 2. So what's the width at this height? Delta x. What's the width at any other height? Delta x. The average of all those delta x's is delta x. So this guy is delta x for a rect function. But it's not delta x for a Gaussian. It's not sigma. Sorry. Yes. Let me start all over again. For a Gaussian, it's sigma. And the average width, the RMS width of the rect is not delta x. That's what I'm trying to say. So first, two things I want you to take away from this. The first is, this is the definition of RMS width. And now your exercise, which we will make a bin for, due 2 days from now, Thursday. okay, is to, on a piece of paper, just like you did for assignment 1, show me what the RMS width of a rect function with delta x is in 1 dimension. Okay? If, of course, you were in 2 dimensions, x and y, the RMS, you could still define the RMS width. But now it would be an integral of x squared plus y squared, according to this, for a zero-centered rect, a 0, 0 centered rect. But that's not, the assignment is for the one-dimensional age. Okay, I want to make sure you understand how to compute RMS width using this formula. You will see that it's not delta x, it's something times delta x, some number times delta x. It's the RMS width of the bar. The 2-dimensional RMS width of the rect function no, say that wrong. The 1-dimensional RMS width of the rect function. Be careful. Will give you a factor for your homework assignment. At least a factor to start trying. Right? The homework assignment requires you to pass it to find a sigma. And that's going to be in your report, right? So this thing in your report says pass in which sigma to bar width ratio you should have used. And I'm telling you that the sigma to bar width ratio that you want to try is the RMS width of the rect versus the RMS width of the Gaussian. Okay, because you're using a Gaussian second derivative. And a reasonable thing to try, oh, I should have made this red. Is to use, I didn't draw it, it's height right. Anyway, the RMS width of that best matches the bar when you're using a Gaussian should be comparable to the RMS width of the rect function, which is a bar after all. And you're using essentially a matched filter, second derivative of that bar, to match the bar that you have in the image and to get us a greater strength. The final comment is, please don't expect yourself to see a final result that is sharply, okay, if you have a bar as your input, let's say a vertical bar of some width. Okay, so you have a bar of some width. So it acts like a rect function in that direction. And you're going to get a result which should be maximum down the middle of the bar. But just because its bar strength is maximum down the middle of the bar doesn't mean that it's like 0 or very small away from that. And so you can check in the numeric values if you're not getting a maximum of your result right down the middle of the bar with respect to that direction, then you haven't done the right thing. Clear what I'm saying? Yeah.
Is it possible if your sigma is too small, that you could get edges, like you could somehow?
You bet. If the sigma is too small, all sorts of, I mean, you can actually compute what you would get. If the sigma is too small, what you're doing essentially is using a match filter that instead of looking roughly like, oops, it's the other way around, roughly like that in cross-section, instead you're using one that looks like that in cross-section. And now you've got all these negative lobes all stuck in the middle of the bar. And essentially, you're going to get a constant times these values. The integral of the second derivative is 0. And so you're going to get a zero in the middle of the bar rather than a rather than what you want. So it's really important to get the kernel, the Gaussian that you use, to have a comparable RMS width to the bar that you're seeking. More questions? Okay, so I've now fixed my, okay, so I'm sorry, I have one more thing to say. Why did I screw up and give you the wrong definition of RMS width? I mean, it's right for the Gaussian, but wrong for anything else. And that is because some research that actually I did, oh boy, this was in the 1970s. Showed the following. Think about taking an image that has white noise, that is to say, the same variance of the noise at every frequency, or equivalently uncorrelated noise between the pixels. So the amount of random variation in this pixel, and is completely uncorrelated with the amount that's in any other pixel, right? Each has a random bit. That kind of white noise is frequently assumed to be the case for images, for input images. But the problem is that when we apply a computed H on top of something that has white noise, it changes the color of the noise. That is to say, it makes the values of the noise at different positions correlated. Put another way, while the noise in X, let's say, in the original image might look like that, the noise in the processed image is still random, but when it's positive, it stays positive for a while, and when it's negative, it stays negative for a while. Put another way, it turns salt and pepper looking noise into blobs, and the blob width here, the widths of these run lengths of the same sign, turns out to be modal, the most common one, at this guy, at the average width of the kernel that you've applied computationally. So you have to realize that when you apply a transformation on input images, it doesn't just change the signal-to-noise ratio, the amplitude of the noise, it also changes this character of the noise, whether you see bigger blobs of noise or whether you see smaller blobs of noise. And so when you're trying to analyze the image, you have to take into account that a blob of these near modal widths shouldn't be thought of as a scene information. It should be understood as noise information. Okay, so you're not going to be examined on this, but I wanted to explain why I had in my head this other definition, because it is relevant to the general problem. For those of you in BME, realize that most medical images these days are processed results. A CT image is reconstructed, an MR image is reconstructed. It involves some processing in the frequency domain and application of some kernel. And so the noise in a CT image or the noise in an MR image is going to have this black picture kind of thing. It's not going to have salt and pepper noise. It's not going to have white noise. It's going to have this blobbishness. And you shouldn't be surprised to see that. Questions on that? Anybody? Yeah, go ahead.
Wait, sorry. He said this, but so what is the relationship with the other form? You know, if both types, you know, is the secondary one the one where you said the noise will block together?
The modal blob size is this average width of positive H and not sigma, not the RMS width. But the RMS width, basically when you're trying to do a match filter, you try to get the same sigma, roughly. The same RMS width, not the same average height. Okay. If you haven't any questions, I'm going to erase all this and get back to our main topic. Wow. Oh boy. This black pen has the best contrast, which means you see it best. And the people remotely in the class are seeing the recordings see it best, but it doesn't erase best. Have to get some water and clean that. Okay, anyway. We were talking now about a new problem, and the problem is compression. That is to say, how do you get a set of basis images that are whose coefficients only have to be sent with a very small number of coefficients of the basis images if you want to transmit the image or store the image. So while you will have capital M basis images, if M is the number of pixels or voxels in your images, right? I want to be able to only transmit some smaller number of those, capital K of them. So instead I'd like to transmit 100 or a few hundred coefficients instead of, if you have 1,000 by 1,000 image, instead of 1,000,000 of them. Is it clear what the problem is? And so the question is, what size are going to be a good size to do that? And what we've said is, what we're going to do is we're going to collect a bunch of example images that I call training images. Okay, and So you're going to have example image number 1, example image number 2. If I'm doing faces, I'm going to take a picture of Mike's face, of Emma's face. Anyway, each of your faces, but I'm going to do that for lots and lots of faces. And so I'm going to have some number of training images, maybe a few hundred. Okay, maybe even 1,000, but not 1,000,000, right? And the number of training images that I'm talking about are going to be careful. I'm going to use little m to mean the number of training images. Okay, so and so each training image has got capital M entries, right? Those are just the row major expression of the image where the second row is put next to the first and the third row is put next to that, and so on. Same thing works in 3D. So this is very long. Each training image is capital M entries, but I get little m training images. And the idea is these training images are going to be used to say that I want, on the average, to make little error as possible in each one of the training images. And if I do that, then I'm hopeful, if they're a good sample, then I will also be making little error in the representation of other images, target images that I want to be able to store. Right? So the idea is the training population should be representative of all the whole population of images. And if I can make low error in the training images, when I say error, when I truncate to only capital K, okay, I only store or send those coefficients. I'm going to have an error, which is for any given image, which is that image minus sum I equals 1 to capital K of AI psi I. This is the approximation truncated to only capital K terms. This is the full image. And what I'm trying to do is to get this to be small as possible. But what I want that to be true for is for each one of the images okay, so for each one of the images, I had sub j, these guys, training. And this is a training image. What I want is the error in that training image to be as small as possible, right? And what I want to do is do the average overall J. I want that to be small. On the average over all the training images, I want the sum of the square errors to be small. That's our objective function. Any questions about what's going on here? Okay. Note that the AI for this particular image J is simply I I sub j training dot psi I. The dot product rule because these are all orthonormal image sets. So the coefficients are computed by the dot product rule. And when you do all the, on the other side up here. When you run all the linear algebra, you end up with the statement that if you want one training image, it's the one that minimizes the average error of the average square error. This is an average over pixels. This is an average over the training cases. So you have an error per pixel squared, and now I'm going to average that over the training set, and I want to minimize that average error. Understand the objective. You want small error on the average for all the various training images. And what I pointed out the algebra that you're supposed to follow in your spare time is that it turns out it can be proven that that's the Arg Max over all unit images. This V is a big M tuple. It's an image of V transpose A transpose AV. That's where we got to last time. What we said was there was a budget, overall, the same budget no matter what set you had. The budget was sum of A sub I squared. And basically what we show is that what you want to do is to maximize the portion of the budget of the sum of squares of the coefficients, maximize the proportion of the budget that is in the first direction. That is in V. So minimizing the error is equivalent to maximizing the portion of the budget. And therefore, if you want to maximize it over one basis image only, right? So this is capital K equals 1. I just want to represent my image by A1 psi 1. That's all, right? What would be the best psi 1? And it turns out that the psi 1, this is a 1, not a prime. The psi 1 is that image that maximizes this. Some of you may not be familiar with the Arg Max notation. I want to make sure you do. If you have a function f of v, let me just say f of x, max of f of x is that value of f that is the largest over all x. Arg Max over x of f of x is the x that produces the maximum. So if I have a function f this is the max, and this is the Arg Max. Right? It's the argument that gives you the max. The argument of the function that produces the max. So this notation here, Arg Max equals 1, this is the image that maximizes this, which we've shown to be equal to minimizing the average square error. Got it? Okay, so what we're up to now is showing that that V that does that is going to be the largest the eigenvector with the largest eigenvalue of A transpose A. So let us first of all notice that this matrix A transpose A is symmetric. Well, we can look, we just check whether it's symmetric, we ask whether its transpose is equal to itself. And AB transpose is B transpose A transpose. So this is A transpose A transpose transpose. But this is just A. So A transpose A is a matrix that is symmetric, right? Its transpose is equal to itself. If you reflect about the diagonal of it's a square matrix. It is, let's see, A is little m by big M, and A transpose is therefore big M by little m. And the result of that is big M by big M. If you have a 1,000 by 1,000 image, we're talking about a 1,000,000 by 1,000,000 matrix. But it's a symmetric matrix, a big symmetric matrix. And what we're going to be first showing is that the eigenvector of that big matrix, which itself is going to be an image, is the one with the biggest eigenvalue is going to be what our psi1 should be, what our very first basis image should be, the one that carries the biggest part of the budget. Well, the first point to make is that A transpose A, being symmetric, has orthogonal unit eigenvectors, capital M of them. Capital M by capital M, any matrix that is symmetric has real eigenvectors, and they're all orthogonal to each other. They're mutually orthogonal. And that's a mathematical result that you should have learned somewhere, and if not somewhere, then here. Okay, so any matrix B orthogonal and square B symmetric and square has orthogonal, say square M by M, has orthogonal eigenvectors. And they're real as well. Turns out that non-symmetric matrices can have complex eigenvectors. And what we're also going to see in a minute is that these eigenvalues that are associated are all going to be non-negative. Okay? And therefore, to talk about the largest one is simply, it's the one with the, all of them are non-negative, and so it's just the one with the biggest magnitude. The eigenvector with whose eigenvalue is the biggest. Okay, so we're going to do a little bit of, first of all, to show that the thing that maximizes this is the eigenvector with the biggest eigenvalue. And then secondly, we're going to understand this eigen stuff better mathematically. Okay? So this whole process that we're talking about ends up being talking about the singular value decomposition of capital A. And it goes by the three letters SVD, and you're going to see SVD in the literature over and over and over again. Singular value decomposition is an important thing to learn from this course. Okay? Okay. On the slides, I'm using little n and big N. On the board, I'm using little m and big M. And the capital M here is the matrix A transpose A. Okay, so we have a symmetric matrix M equals A transpose A. I'm sorry for the duplication of that symbol, because I also use capital M as the number of pixels, and it's not the same thing. Sorry for the double. Okay. It turns out that any matrix M, sorry, let's start all over again. Where are we here? Right. Any matrix, not a symmetric matrix. We are going to be dealing with symmetric matrices, but I'm talking about any matrix M, which is going to be little n by big N. And it could be little m is like so, and big M is like so. Or it could be little m is equal to big M. Oh, sorry. And n, where little n equals big N in a square matrix, right? We're talking about any matrix at all. It doesn't have to have the same number of rows as columns. There's particular cases where it does. So-called square. Turns out it can be understood in terms of our good old friend rotations. So if you think of what a matrix, an n by n matrix's job is, okay, so here's this matrix M. Its job is to take in an input, x, which is n by 1, a column vector, and produce a little n by 1 result, mx. Right? It's just a mapping from input positions with capital N entries into result entries with little n entries. That's its job. It's a transformer, a linear transformer from big N vectors into little n vectors. So if, for example, big N equals 3 and little n equals 2, we start off with a vector in 3 space. It's got 3 entries, right? And it maps into a plane, right? So for every vector in 3 space, we map it onto some position in a plane, some plane. A 3 space into a 2 space. If m equals n, we have a vector, and it maps in 3 space, and it maps into another vector in 3 space. M's job is to map vectors into vectors where the inputs are in capital M space, capital N space, capital N space, and the outputs are in little n space. Okay? Okay. But wait a second. Remember this coordinate system business. We had a basis coordinate system, an initial coordinate system, which might be considered the EX, the EY, and the EZ for 3 space. And we could play the same game with a different coordinate system, but then there's a different matrix that's going to be applied. And that new matrix is still going to have the map, let's say 3 space into 2 space, but you got to be careful. You got a coordinate system in 3 space that's relevant and a coordinate system in the 2 space that you're mapping onto. And you got to specify which coordinate systems you're using, or you don't know what you're doing. Okay, so assuming that both initial coordinate systems are some x, y, z for the first one and x prime, y prime for the second one, if you're mapping 3 space into 2 space, I need a coordinate system for x, for x prime, y prime, and I need a coordinate system for x, y, z. But we're mapping x, y, z's into x prime, y prime. We need coordinate systems for each. And each one of those coordinate systems is simply going to be a rotation of the ordinary xy coordinate system. So in 3 space, we're going to have a 3 space rotation that determines the coordinate system we're talking about in 3 space. And in 2 space, we're going to have a coordinate system rotation in the plane that is mapped to, right? And what this says is that it's a big deal. That first full line, the second line on the slide. What you do when you're mapping a matrix is you're going to have a rotation of your coordinate system in n by n. So this is a matrix that produces a rotation of the coordinates. And it does so on capital N vectors, on the input vectors. And once you do that, you're going to have a gamma, which is going to be little n by n. And then there's going to be, this is an n by n rotation. And this guy is little n by little n rotation. So this thing takes care of the coordinate system in the output space, and this thing takes care of the coordinate system in the input space, right? And so if I have a 3 by 2 matrix, I'm going to take my vector that I originally specified in x, y, z coordinates, and I'm going to modify that vector by rotating it into the new coordinate system in 3 space. That's capital S. And then I'm going, once I have those new coordinates, I'm going to have this n by n diagonal matrix that I'm going to explain now. That's going to produce you a new vector in little n space. And then I'm going to rotate that vector that's now in little n space by a rotation in little n space. That's capital R, is an n by n rotation. What's this gamma thing? Well, if it's, let's take 3 examples. This kind of a rectangle, this kind of a rectangle, and a square. Now you're used to a diagonal matrix in square. It has values along the diagonal and 0 everywhere else. Okay, that's an ordinary square diagonal matrix. And all that's going to happen for non-square matrices is still going to start out at 1, 1, 2, 2, 3, 3, but it's going to end at the extreme here. Oh, what is this? This is, the situation is this. This is little n. This is little n equals big N and n. And this is n and n. And so the point is you're going to get 1, 1, 2, 2, 3, 3, 4, 4, all those indices that have the same x index and, first index and second index, but you have to stop wherever you run out of indices on that, in that. Okay, so what does this do? The action of this matrix is to take the first coordinate, the first transformed coordinate, transform meaning it's in this rotated coordinate system, and if you multiply it by, if the value is 3, you're simply lengthening that vector by 3. And if the next entry is 4, then you're lengthening the one in this direction by 4. And if you have, in our example, where you have a 3 by 2, you're going to be lengthening some of the vectors by 0. Huh? Lengthening a vector by 0? Well, it just means I'm collapsing the space, right? If I have a 3 space, and I have a component of the vector that's in a direction that is multiplied by 0, it's all going to, it's just no longer going to have any component in that direction. So if you had a 3 space and you've got this 2 by 3 thing, what's going to happen is one of the directions is going to be multiplied by, say, 3, another one multiplied by 4, and a third one multiplied by 0, which leaves you only a 2-dimensional space. Right, so these 0 multipliers of this diagonal matrix are space collapsers. They lower the dimension of the space. They turn a 3 space into a plane, for example. So, this so far is going to say for any matrix any matrix capital M, M can be written as a rotation of the coordinate system in the input space, a collapse of the space possibly, and stretching or contracting. You can multiply by 1/3, and it contracts the vectors instead of expands them, right? You multiply every vector in that, the component in that direction by 1/3. And it can be negative too, which means it flips this, the vector in this direction flips to negative direction and gets multiplied by the magnitude. And then there's a rotation of the coordinate system. The easiest one to understand is when little n equals capital N. Okay? And when little n equals capital N, then we have all these entries. And each one of them can be a positive or a negative or zero number. But normally all non-zero, because otherwise you're going to collapse the space. There exist singular transformations that collapse the space even though you have a square matrix, and they will have a zero in one of these diagonal elements. And what happens, I'm going to draw 2 space to 2 space. And, over here. So here is, let's see, big N equals 2. Here's little n equals 2. And I'm going to make a little unit circle about 0, 0. And what we're going to be able to show is that this little unit circle turns into an ellipse and a specific ellipse. And what's going on is that the eigenvectors are going to be the principal axes of the ellipse. And the stretch factors are going to be the length of these radii. If this thing is 1, and this thing is, is 2.5, then the eigenvalue, did I say eigenvector? The eigenvectors are the principal axes of this ellipse, and the eigenvalues are the multiplying factors, the radii of the ellipse. So the radius of 1 in x goes into a radius. Okay. And so what this is saying is, I'm going to take this unit circle, I'm going to rotate it by some angle, so that, and then I'm going to expand in that new coordinate system by the eigenvalues. And then I'm going to have an output. Now I'm over here, and I'm going to have an output that rotates. So one way to understand it is this coordinate system, if it were flat, and this, I don't say this. The idea is to put this in a coordinate system so that the expansions are in x prime, y prime. And then you're going to take those expansions this way. So rotate this so that the expansions are this way, and then we're going to rotate the ellipse back to where it comes from. To make a long story short, every matrix multiplication can be understood as a rotation of the input coordinate system, an application of stretch factors along the new cardinal coordinates, the x prime, y primes that we've rotated into, and then a rotation in the output coordinate system. And that's easiest to understand in n space. And so now if instead you're in 3 space, this is a ball, right? This is a unit sphere. And the unit sphere goes into an ellipsoid with 3 major axes, which are the eigenvectors of the matrix transformation. Put another way, if M is square, this thing are the stretch factors. They're the eigenvalues. They're just how much the unit vectors in the respective directions are that. And this rotation gets you so that the eigenvectors are all along the cardinal direction. So they were somehow like so. You're getting them to the cardinal direction. The gamma multiplication now stretches them all. And the R rotates you back. But for the particular case where things are square, you get the special situation where the rotation, the original rotation, and the final rotation are just inverses of each other. So if you're mapping 3 vectors to 3 vectors, you're going to rotate your coordinate system, or put another way, so that this coordinate system is now the cardinal coordinate system. You're going to do the stretch factors on each one of the directions, and then you're going to rotate back. And for a rotation matrix, let's be careful what a matrix does. If you have a coordinate system, let's see what it is. If you have a coordinate system EX, EY, EZ, but EX1, EX2, EXN. Okay, so this is a diagonal matrix, right? It's got a 1 in the first place, 1 in the second place, 1 in the capital N place, and 0 everywhere else, right? And what M does is it rotates, what a rotation matrix does, what R does, when it applies, it maps EX1 into U1, and EX2 into U2, and EXN into U1. It just, so columns are just the images of the respective cardinal vectors. So X1 goes into that, U1. EX2, diagonal to that, goes into that cardinal direction. I mean, that U2 direction, and so on. These rotation vectors are like that. And for a square matrix, R inverse equals R transpose. That comes from the fact that the dot products are all 0 for when you dot product the 2 vectors that are in different columns, and they're one when you dot product something with itself. So, guess what? These guys, it or its transpose, are the eigenvectors. The rotation matrix is just the list of eigenvectors. Right? Because what you're doing is you want to diagonalize our square matrix. And to diagonalize it means all that's going to happen is it's going to have expansion in the x direction, expansion in the y direction, expansion in the z direction, if it's a 3 by 3 matrix. And if you have pure expansions in each separate direction, that's the Eigen property. Okay? So the upshot is the R matrix gives you the eigenvectors, and the G matrix is the eigenvalues. So now when somebody runs Eig, you run Eig, on a matrix, you will understand that it produces a rotation matrix, which is just in its columns the eigenvectors, and it produces a diagonal matrix, well, a list, which is just a list of eigenvalues. They're the expansion factors. Okay? Okay. So, if we're going to apply a matrix, what vector in all of the possible unit vectors is going to get expanded most by the biggest factor? The one with the largest eigenvalue, right? If you have the eigenvalue 7, 5, 2, a third, whatever, the one that will be expanded most is the one that has eigenvalue 7. Any component that is in any other direction, like one that's only expanded by 4 in that component, well, you'll only be expanded by 4, which is not as, if it's a unit vector, you have to, how do I say this? You have to take away from the size of the one that was in the first eigendirection to make a unit vector that's in something that has a component in some other eigendirection. And so rather than all of the unit be multiplied by 7, some part of it will only be multiplied by 4, and that won't get expanded as much. Right? So the basic idea here is that what we're going to want for our A transpose A square matrix is to get the biggest expansion, which is what this V transpose V, A transpose A, V does. It says, how is that going to be most expanded? And the answer is, you take the eigenvector of A transpose A, the square matrix, and that's the one that's going to get the biggest expansion, which is to say the biggest proportion of the budget that we have. Okay, so I want to come to the end of this teaching section. We've learned something important about matrices. They all can be written as a rotation of the input space, a set of expansion factors that could be positive or negative or 0, and another rotation in the output space. For square matrices, we've seen that the two rotations are inverses of each other. You rotate this way, you apply expansion, you rotate back. And that was the basic linear algebra result. that you should learn. If you haven't had that math now, you have had it, and this is going to be something I'm expecting you to know. Every matrix can be written as R gamma rotation. And then the final thing that we've learned is that the particular direction that we want V to be in for our biggest portion of the budget, which minimizes the error most on average over the training cases, is the eigenvector of A transpose A that has the biggest eigenvalue. Okay? The final things will go on. Next time I'll talk about what happens in these non-square cases. And we're also going to see that I've just indicated we have to do eigen analysis of a 1,000 by 1,000 matrix, and we don't want to do that, or sorry, a 1,000,000 by 1,000,000 matrix. If we have a 1,000 by 1,000 image, then the matrix capital M is 1,000 squared by 1,000 squared, 1,000,000 by 1,000,000. We don't want to do that. How can we solve that problem faster? And we're going to see that we're going to be able to do a little m by little m eigenproblem rather than a big M by big M eigenproblem. End of lecture. Sorry to run you over. Yeah.